We're going on now to the PowerPoint slides of Chapter 9, Section 6, Solving Exponential Equations and Logarithmic Equations. Now, a good thing, of course, in any of these, as we did them, was to look at your textbook, look over it. You can look at the video I prepared. This is what we'll be using in class, and it's sort of an outline of what is in our textbook. So first we'll look at solving exponential equations, and let's look at some examples of them. This is an exponential equation where the x is the exponent. Here's another example where the x is part of the exponent. Now, in an earlier section, we did solve some of these by using a special technique, which is explained by this slide. That is, when you have a base that is equal to the base, then your exponents are equal to each other. And they're saying the base cannot be a -1, a 0, or a 1 for this to operate. Powers of the same base are equal if and only if the exponents are equal. So what we do is we take away the bases and have the exponents equal each other, and that's what we solve. So let's take a look at our first example here. Now some of these are long, so I won't do them myself, but this one I would. So here we have 5 to the x power is equal to 125. Now as you look at this, are the bases the same? No. So what do we need to do? Well, we need to fiddle with this one to get it to be a base of 5. And 125 is what to the third power? And the answer is 5. So now our bases are the same, and our exponents should be equal. And that is the solution. So if x is 3, 5 to the third power is this. Now again, this is more to show you the process. This was a super easy one. And again, take notes so you see what we've done. The key here was to convert this to a base of 5 to some power. And that's what they're showing here. Now, the principle of a logarithmic equality is for logarithmic base a, and for x and y is greater than 0, we have when these exponents are equal to each other, we can convert this to an equivalent logarithmic format, which is what we've done here. So there's our x, there's our y, and we've just added log base a, log base a. Okay? So here we have a basic example of it, and I'll do this one too here. So we're going to go log 3x plus 1 equals log of 43. Now, one of the techniques we had earlier in Chapter 9 was when you have a log with an exponent, we can take this exponent and move it to the front. So it now becomes x plus 1. And we could, I don't know if we can put that in parentheses, maybe that would be fine. Log 3 equals log of 43. Now we want to isolate the exponent on this side, so we're going to divide both sides by log 3. So here these cancel out, and I'm left with x plus 1 equals log 43 of log 3. Now we want to solve for x, so we're going to take this item and move it to the other side, where it changes its sign and becomes a negative 1. So we then have x equals this. Now, to get your final answer, what you do is you put log of this into your calculator, divided by log of 3, get an answer, then subtract 1 from it, and that will be your approximation. Remember, this is the exact answer, and what you get out of your calculator, that's an approximate answer. So let's take a look at it here. So there's that. We put log in front of each one. We're going to then take this exponent and put it in front of the log. Then we're going to divide both sides. This is the part I don't like the way they've written this. I like it right underneath there. I guess they're typing this out, so that's why they did it. You're transposing the positive 1 to the other side, becomes a negative 1, and then this is the approximation. Now originally this was a 3.4, and then they subtracted 1 from it and got the 2. And that is the answer, and if you put that into your calculator, graphing calculator, this is what it looks like, and it intersects there. Y sub 1 is this curve. Y sub 2 is just a horizontal line. They intersect there. Okay, we're going to take a look at this one now. And again, there was one very similar to this done in our textbook, but let's take a look at it. This is in natural logs. So since it's a natural log, we'll just convert it to a natural log. ln of e, and then 1.32t equals the natural log of 2000. Now, we had said that there was a sub e here, if you recall, that this just cancels out and becomes a 1. So we're going to write this then as 1.32t equals the natural log of 2000. So to solve for t here, and this is critical, and by the way, take notes on this. This is the model you will use. You're going to divide both sides by 1.32. and you will get t then. You put natural log 2000 divided by this number, 1.32. This is a regular number, and that will give you, again, your approximation, which, when we look at it, and again, it's divided by this, they're using that diagonal line, approximately 5.7583, rounded to 4 decimals. And I don't know if you recall that logarithmic and exponential functions are inverses of each other. We did a lot of graphing of this earlier. And again, these would be your graphing of these two equations using a graphing calculator. So again, the summary of solving equations of this form, where you want to solve for t, take the logarithm, whether it's natural or common, this would be e, this would be base 10 of both sides. Use the power rule for exponents so that the variable is no longer written as an exponent. Divide both sides by the coefficient of the variable to isolate the variable. If appropriate, use a calculator to find an approximate solution in decimal form. One of the examples we did in the textbook, they apparently wanted us to leave it the way it was, not in a decimal approximation. Okay, again, solving logarithmic expressions are called logarithmic equations. And what we do is we change this now into its exponential form. So we had said, and this is just some background that I think might be useful. If we had the log of some base, and then we had some number here, that was equal to the exponent. So we said the log of our base, which in this case is 2, let's put it right there as 2, is going to equal, this would be our answer, this is our exponent, which is 4, that would equal this. So we have converted from a log form to an exponential form. So what do? Well, we expand the 2 to the 4th, which is 16. Now we're going to transpose that. When we bring the 5 over, it changes its sign, becomes a negative 5 here. So this gives us an 11 equals 6x. We're going to divide both sides by 6. We get x equals 11/6. So again, we started with a logarithmic equation. We converted to a exponential equation, and we solve for our variable. So again, log base 2 raised to the 4th equals our answer. Transpose the 5 becomes a negative 5, 11. Divide both sides by 6. Again, I don't like the way they're doing that. And that gives us 11/6. Again, that's not a nice way to do it, but I guess that's the way they do it. Okay. And the check does work out. Often the properties of logarithms are needed. These were properties we've worked on step by step. The goal is to first write an equivalent equation in which the variable appears in just one logarithmic expression. So we're going to do some factoring in a sense. We then isolate the expression and solve as in the previous examples. Okay, so here we have the log of x plus the log of, in parentheses, x plus 9 equals 1. So let's factor out. And by the way, there is base 10 there, base 10. So we write it like so. And again, you should be taking notes on this. This is a model that you will use which you will have some like this. So we're factoring out the log of base 10. So that leaves us with an x times this, which will equal 1. And then now we're converting this from a log, as we did prior to this. Let me show you how to do that. So base 10 is to what exponent? Well, base 10 is right there. To what exponent? 1. There's 1. So what is this? We don't usually write a 1. It's just going to be 10. And it equals this. Okay? So now this becomes x squared plus 9x. We're going to transpose the 10. That becomes a negative 10 equals 0. Now, how do we solve these? Well, we could complete the square. We could use the quadratic formula, but this factors, so we'll just factor it. So we get x and x, 10 and 1. This is negative. This is positive. So this will have to be positive, and this will have to be negative. So we now use the principle of the zero factor here. X minus 1 equals 0, or x minus 10 equals 0. Well, how about x plus 10? Yes, that's much better. Watch the signs, because that's going to make a major difference. You'll see here in a moment. X equals a positive 1. X equals a negative 10. Okay, now what we have to do, and let's just follow it some more here. And we lost it a little bit down there toward the bottom. Let me move that down for you here. See it? Okay. Now, notice when we do our work here, we only get one answer, because there is a problem. There's only one point of intersection at 1, 1. So I'm going to go back, actually. I want to show you this. If we were to take this value and put it in our original equation here, and we're saying here the log of negative 10. Can you have a log of a negative number? No, these are undefined. So just looking at this would wipe out the possibility that that could be an answer. And then the graphing is proving that it could not happen. Okay, so there's only one point of intersection. And here is the proof of it, that when you try the negative 10 in there, that's false. The logarithm of a negative number is undefined. So the only solution is 1, even though you ended up through the algebra to get 2. That's why you need to check them. Okay, let's check out this one now. Again, you want to take some notes. So how would we do that? Well, we're going to factor this out like we did before, and they did a nice job here, so I'll watch them except for this part where this should be written x minus 1. Then you don't need this arrangement here. Okay? Remember, subtraction in this model is division, which is what that bar indicates. So then we're going to convert this from logarithmic form to exponential form. Our base is 3, goes right there, and that's our exponent. So when we square this, this is going to become a 9. We're going to FOIL this. Well, no, we're not foiling it. See, we're going to divide that. So again, not doing a different one we would FOIL, but not this one. This is division. That's why I don't like it written this way. All right. So actually what they're going to do is cross multiply. I showed that in the textbook version. And you get this, you distribute, and you get that. Okay. So we're going to bring the x's over to this side and get a 7x. Bring this over to this side and get a 12. And then we get x equals 12 divided by 7. That really upsets me here seeing this, but what are you going to do? And they're leaving the check for you, and it does check. Okay, well, this will wrap up our lesson. We're going to be doing some additional exercises now that is the proof. As you work examples, can you get the answers?